This is part 2 of the Lahendong case study. We used our technology to perform the visualization and interpretation of the three-dimensional distribution of the temperature gradient in the Earth's interior and compared our constructs with the open source data about numerous wells drilled within this geothermal area in Indonesia. The positive integration and convergence of Terra's 3D volume with the actual facts from the productive and non-productive wells demonstrates Terra's technology possesses a powerful predictive capability in geothermal exploration. This is a 25.5-minute presentation. Part 1 of our analysis deals with the regional geothermal setting at Lahendong and ends with a 4-minute mark. Feel free to fast forward to the discussion on the temperature gradient distribution and interpretation between minutes 4 and 7, or to the review of the actual well data starting with the 7-minute mark. Thank you.
So the regional result of the study is a regional 3D volume thermal energy distribution at the surface. The regional analysis uncovered 5 to 7 different geothermal prospects, and at this time we will be concentrating within the small area where all these wells were drilled. What you see here is a temperature gradient. So each point in the subsurface represents a focal point corresponding to a circle anomaly at the surface. Such an anomaly is computed by processing pixels reflectance. Here is a 3D volume, of isotherm surfaces within this area. Isotherm surfaces of the temperature gradient, The isotherm surfaces of the same color represent similar values of thermal gradient. For example, high gradient is purple color, indicates for a contact zone of hot rocks and inert bodies like water that is being heated. Lowering the gradient, please see the purple and green at the top of Lahendong caldera indicating the heat exchange. Purple usually means that there's high degree of heat transfer. We then superimpose known faults and lineaments with our data set, with our regional cube, in order to make certain conclusions, which will be apparent very soon and later in this presentation. We were very pleased to say that the locations of faults and lineaments that were delineated utilizing the STEP technology and our interpreters very well correlated actually with the lineaments and faults from the open source data. All of these lineaments and faults are integrated into the 3D cube for interpretation purposes. Within this presentation, you will see varying stages of this interpretation and varying conclusions that are being made so that we can then put together an accurate picture of what is going on within this area, and specifically within this geothermal volume. So what you see here are different faults that we inserted into the 3D volume. In this case, this is the 3D volume of the distribution of geothermal gradients. And some of these conclusions will be seen in a short while. We try to reduce the regional view, a very large area view, to the local Lahendong feature, making it possible to visualize its position within the regional fault system. You will see actually that the southwest-northeast fault, the southwest of the Lahendong caldera, depicted in the open source literature, can also be traced in the subsurface utilizing the 3D volume shown here in this particular plane right here. So that is a very good sign that our data set is accurate. Please take a look at this particular fault plane and how well it correlates with the fault plane delineated here. Further interpretation of temperature gradients helps classify the volume into geothermal reservoirs and zones of favorable geothermal conditions. In the center of the volume, you see it right here now, there are two zones of uniform temperature gradient. Both zones appear to be encapsulated with a zero temperature gradient, which actually is clear. It's clear space for the purposes of good representation, good graphical representation. Both of these zones, and especially this zone right here, are shown with a zero gradient, indicating for a potentially convective fluid reservoir. Convective versus conductive. This one, in our opinion, is convective. Low temperature gradient values, which is red in color, right, indicate for minimal heat exchange and serve as heat barrier. We're actually looking for very low or close to zero temperature gradients, which would be indicative of convective reservoirs. High temperature gradient zones, for instance, the ones depicted with blue and purple color in the interior, indicate for a source of heat. So the ones that you just saw in purple color indicate for a source of heat, such as the one shown right here at the bottom left. As a general rule, okay, isolating the red zones as potential caprock or heat barrier zones can help delineate the reservoir and determine favorable drilling conditions. In this particular case, we believe this is a favorable drilling condition. In other words, we have a heat source at the bottom, we have an encapsulated zero gradient zone at the top. So to us, it looks like a zone that is potentially favorable, or as we call, convective. Right above the heat source, there's also an interesting zone. It's a thin zone. However, right above the heat source, it may be very hot and also very favorable in terms of being convective. Showing other values of temperature gradient helps interpret not only the reservoir geometry, but also direction of heat transfer and heat source. Please note, within the unfavorable area, the heat exchange is steady to the surface, right here. Medium value of thermal gradient, denoted with green color. Nevertheless, it's very high as compared to what it should be for convective conditions. Therefore, such an area would clearly be called a conductive area, according to the STEP technology. Let's take a look at two particular wells, or their locations, and how they fit into the logic of convective and conductive areas in connection with finding the geothermal deposit. So LHD4 and LHD15. So LHD15, the bottom hole location is right here, right in the center. LHD4 is a straight hole, and its bottom hole location is right here. It's a straight hole right here. So both of these penetrate this convective zone, as you can see right here. And of course, because they penetrate a convective zone, and it is our belief these wells may be productive.
Comparing the STEP results with the drilling results of both LHD4 and LHD15 wells demonstrates the validity of the STEP construct. The aforementioned convective zone, shown in the image on the right as a near zero gradient transparent area encapsulated in the red color, begins at 200 meters below sea level and ends at approximately 1,500 meters below sea level, which is the target depth for these wells. Please note that the graph shown on the right for LHD4 precedes the STEP study by several years and shows that LHD4, just like LHD15, is convective between the depths of approximately 200 and 1,500 meters below sea level. Thus, the drilling results and the graph precisely validate the STEP construct.
There's another favorable condition, And that favorable condition for geothermal applications is physical properties of the geomedium, how permeable it is. Interpretation of physical properties of the geological environment helps classify the volume into permeable reservoirs as zones of favorable geothermal conditions. Permeable zones indicate for circulation losses, for instance, drilling fluid going into the formation, although they do not directly inform about geothermal reservoir fluid charge, means production. Be as it may, permeable zones are very important as very often they correlate with great geothermal productivity. Permeable zones at a high enough temperature are good indirect proxies for production feed zones. Okay. Temperature gradient may be conductive in a reservoir with low permeability that inhibits fluid convection. A well that is hot enough to potentially produce may not be productive because of low permeability, which is why this is a very important component to consider. Let's take a look one more time at wells LHD4 and LHD15. We could clearly see that permeability within the wells LHD4 and LHD15 right here is medium. It's medium permeability area. There's some tight rock above it, and there's also some tight rock below it with a very high permeability area at the bottom of it.
Please note, this area below the convective medium permeability production zone is the zone of high permeability and temperature gradient, which is consistent with it being a heat source.
Let's take a look closer. The middle of our main reservoir is of medium permeability. Okay. The bottom and the cap of this reservoir, or at least of this particular formation, is tight, low permeability. Perhaps it serves as a very good seal. Perhaps that is the reason why this entire cavity has zero or close to zero gradient at the top. It probably indicates that this tight rock right here serves as a pretty good thermal barrier. And of course, this is the heat source, high permeability area at the bottom. At very deep horizons below 2,000 meters below sea level. Let's take a look at another well, which is LHD number 13. It's a straight hole, and it's a deep hole. It is one of many wells of its own cluster. Let's take a look at it. Within this 3D volume, you obviously identify right away that it penetrates, an area that, according to our rules, is convective, and it also penetrates another area right below it, okay, which is above a substantial heat source, and that area also appears to have low gradient, and it may be convective. At the top, there's a zone of high gradient, which probably is not a zone of interest. It looks like a conductive zone between 0 and 300 above sea level.
Let us examine the well LHD 13 with the depth ranges of its conductive and convective zones on the step constructs as compared to the graph of measured temperature versus depth on your right. The cube of the temperature gradient distribution shows the well is conductive between 500 meters above sea level and 200 meters below sea level. The graph on the right confirms it. LHD 13 in fact displays a shallow linear conductive gradient in this depth range. What about the deeper depth intervals? LHD 13 appears to be convective between 200 meters below sea level and 1,000 meters below sea level, which is consistent with the graph on the right. The measured temperature versus depth graph also shows the well is very hot and convective below 1,200 meters below sea level, which is very consistent again with the behavior of the temperature gradient within the zone located right above the heat source, which is shown by the extreme temperature gradient at approximately 3,000 meters below sea level.
Let's examine the permeability cube within well 13. If you remember, the main reservoir has decent permeability characteristics, medium permeability characteristics. The bottom, so the bottom part of this of an additional reservoir actually does not have good permeability characteristics. So although it appears to be convective, although it appears to be convective from the previous study, take a look please. It's pretty tight. So it is likely that in a situation like this, because it is so hot, okay, it is likely that this area would be producing, very hot and still convective, although the reservoir quality remains an issue. We're summarizing the condition of the well right here. High permeability zone, potential loss of circulation right here, shallow. Medium permeability between 0 and 1,000 meters below sea level. Low permeability between 1,100 meters below sea level and target depth, as shown right here at the bottom right. Let's take a look at another well. This well is number well LHD 6. All right, so LHD 6 well is right here. You could see a line. There's not much else to say about this well, because this well, as you saw previously, is located in a high gradient zone. And as such, this well is most likely not of interest to us. To summarize it, LHD 6 is a well that has high temperature gradient and is behaving like a conductive well.
The graph on the right confirms that this well is of no interest from the geothermal exploration perspective. It is purely conductive.
Let's take a look at another well. This well is LHD 1. LHD 1 is located in a very seems like a very busy area tectonically speaking, although we cannot infer it from looking at the just this particular 3D volume. Be as it may, most of it, as you can see here, apart from apart from this area in the middle, most of this wellbore appears to be conductive, although it is sitting below a fairly large heat source, so it may be hot, but it probably is conductive.
The graph on the left totally supports the 3D volume. The well is hot and near boiling in the shallow aquifer area and hot conductive in its deep horizons.
Let's summarize. High temperature gradient, conductive versus zero temperature gradient, convective. Within LHD1, it is very difficult to interpret the permeability map or permeability 3D volume within this area or within the wellbore LHD1. As you see, there's many changes in permeability occurring here, and they can indicate for many other things like potential lithological changes, fracturing, tectonic changes. Let us take a look at something very interesting. What you see here are the isotherm surfaces that were created utilizing temperature data from the open sources. So temperature measurements from within the wellbores. As you can see here, we have, a hot area right here, and we know that it is, at this point we know it's one of our main reservoirs. And then we have a cooler area. But let's take a look how the isotherm surfaces correlate very well with zero gradient surface, validating our zero gradient surface, okay, for a cooler temperature regime, which is toward my right at this point, or toward LHD6. We already noticed that LHD6 was a conductive well. It was not a part of a convective or geothermal reservoir or an area of a zone of geothermal interest. So this is very interesting. There's also, these also surfaces, they curve a little bit, and so this curvature may indicate that actually there is a, or validate this fault plane. So let's take a look at the images one more time. These are isotherm surfaces created utilizing temperature data from open sources. As you see, there is a very strong correlation between the isotherm surface and the outer zero gradient surface that basically validates the isotherm surface, or vice versa. They validate each other. So certainly the well data very well correlate with the step construct. Well number 6 right here, if you remember, it was in a conductive zone. Bottom right is showing again right here. And as we can see now, it is in a cooler space. We see here again the isotherm surfaces created utilizing temperature data from open sources. There's a few different conclusions that I would like to show you here. Right now we are showing you the faults that we were able to insert into this volume. As we said, these faults, most of them correlate very well with the faults found in open sources as well, but these are the faults that we delineated too. So as you see, there is a very good general correlation. I'll go back of this particular fault. This particular fault correlates very well with actually the cool surface. So the main reservoir associated with LHD4 and LHD13 clusters is confined to a separate fault block. LHD6, as we know, is confined to its own fault block. LHD1 is confined to its own fault block, and well, LHD2 is confined to its own fault block. We superimpose here temperature gradient constructs with the rest of the data, and as we discussed, the correlation is evident. Let's take a look at the static pictures. So this fault right here, all right, separates the cooler zone. Well, LHD6 is in its own separate block. Let's take a look. The clusters of wells LHD4 and LHD13 are located also in their own separate block. Well, LHD1 is located in a separate block. Well, LHD2 is located in a separate block. Perhaps all of this explains that LHD1 and LHD2 are outside of the main reservoir. So, ladies and gentlemen, this case study clearly demonstrates and validates that STEP technology possesses a tremendous predictive capability. And in this particular case, we were able to show you and infer with reasonable accuracy tectonic blocks that are of interest, geothermal interest, thermal gradient conditions that actually can be interpreted and for that purpose inferred into zones of conductive and convective conditions. We can also find heat sources, especially deep heat sources, and permeable zones, which play a big role in finding geothermal production. Thank you very much.